Okay, let's get started. So today we're going to be doing the last bit of stuff for volumes. So that is the washer method and the shell method. Tomorrow we're going to do some mixed problems. So some problems from disk method, washer method, and shell method. But they're all going to be mixed up, and I'm not going to tell you which method to use. Okay, so that's how it's going to be in the test. I'm just going to give you the setup. You need to find the volume. So part of the marking allocation is figuring out, do you use the disk method, the shell method, or the washer method? And then the rest is up to you, okay, to pick that. We'll see some of these problems you can do multiple ways. So a few of them you can do using the washer method and the shell method. So there's two ways to do that. Remember for the test, if there's two ways to do something, you get the marks for both. So in the class test coming up, if I give you a problem where you can do it using the washer method and the shell method, again, I'm not telling you which one to use. You can do one method, get the marks. Do another method, get the marks for that as well. Okay. So that will come up for the volumes part for class test 2. Any questions on that? Oh, good. Okay. And then the same thing will be for the quiz. So remember, next week is the holiday. The week after, we have quiz 8 on the volumes. Again, if the question can be done using washer or shell, you can do both, get the marks for both. Yeah, but that'll be for later. I'll get to that later on. Okay, so let's go through the washer method first, and then we'll go through the shell method. So when do we use the shell, the washer method? So we'll look at a very simple example first, just to get an idea of how to do this, and then we'll look at the more complicated examples. So we have the following setup. We've got this function here, root x, and this other function x squared. Okay, so y equals root x at the top, y equals x squared underneath. And we are going to rotate this around the x-axis. Right, you know the setup. You've got a region, you rotate it around an axis. It's going to make some 3D shape. We want the volume of that shape. Now, this is a little bit different to the disk method because the shape that we produce is not entirely solid. Right, that blue region, when we rotate it around, that's going to make some solid shape. But that region underneath, below x squared, that's going to make the 3D shape hollow inside. Okay, so we'll draw a little sketch of this, and we'll see that part where it's hollow kind of makes things a little bit more difficult. Okay, so we'll start with the outside part, that root x. If we rotate that around the x-axis, we're going to have some kind of bowl sort of shape. So it's going to look something like this. Okay. I hope everyone can imagine that. You rotate that root x around, you end up with that kind of shape. But notice that x squared, when we rotate that around, that's going to make a hollow part or a cavity in our shape. It's going to end up being something like this. So it kind of goes in a bit there. So this wall over here, that's solid, right? From that blue region being rotated around, that's going to be solid. But there's some inside part that's hollow. So this part here in pink, that region underneath there, that's empty space. So when you rotate that around, this inside part here is going to be hollow. Okay, so you end up with this hollow cavity inside the solid. That's the biggest clue where you need to use the washer method instead of the disk method. So remember, for the disk method, the shape was always solid, right? It was like a solid bowl, a solid cone, a solid sphere, something like that. But in this case, you've got a hollow part inside. We can't use the disk method, right? Those disks were solid. You can't have a hole inside. So instead of using the disk method, we use this new method called the washer method. Okay, so how does that work? Now, again, we've got this axis. Remember, when we're doing our cross sections, we cut along the axis. So we're going to do the same thing here. So we've got the x-axis running through the shape, and we're going to make vertical cuts. Make vertical cuts along the shape. That's going to give us our cross sections. Okay, so let's look at one of the cross sections. So we're looking along the x-axis at our shape, and we've cut it. Okay, so what do we get? On the outside, we're going to have a circle. From root x being rotated around, that will be a circle on the outside. So here we're looking at the cross section. So on the outside, that's from the root x being rotated around the x-axis. But we also get another circle that's a little bit smaller from x squared being rotated around. Okay, so let's label some things here. So again, that blue part being rotated around, that's going to make the solid part. That's going to end up being this bit in our diagram. Again, you need to imagine slicing this. So that blue part being rotated around, the cross section looks like that. And then the pink part, that's the hollow parts being rotated around. That's going to make this inside part here. Okay, so we end up with this shape here, which we call a washer. If you've done any plumbing, you know what a washer looks like. It's like a disc and it's got a hole in the middle. So you've got a washer like that. And there's two radii. So we've got an inner radius for the pink part and an outer radius for the blue part. So let's just sketch that in here. So we've got an inner radius and we have an outer radius. Now, how does that match up to our original diagram? Remember, this is being rotated around. So that pink part is the inner radius. That's going to be this distance over here. Let's call that R in for inner radius. Does everyone see that? So the inner circle in pink, that corresponds to that distance up to x squared when we rotate that around. What about this outer radius from the center to the end of the blue part? That's going to correspond to this distance. Let's call that R out, so outer radius. Okay, does everyone see that? How we get from the diagram to the washer? Okay, so we rotate it around. From the x-axis to that first curve, that will be the inner radius, because it's the smaller radius. From the x-axis up to the second curve, that will be the outer radius. That's the larger one. Okay, you rotate that around, you get that washer shape. Okay, so what's the volume of this going to be? So the volume is going to be the integral from a to b. We'll see what the bounds are in a bit. We need to find the volume of just that blue part, not the pink one. Remember, that's hollow. We must remove that. So we're going to find the volume of the full shape with the outer radius and take away the volume of the smaller shape. Because remember that pink, we remove that. So we do the volume of the outside. So it's a circle, so pi r out squared. That will be the outer volume. And remember the pink part, that's hollow. We want to remove that. So it's going to be minus the volume of the pink part. Okay. And here our cross sections are along the x-axis. So when we add up the cross sections, we add up along x. Okay. So we end up with that. Okay, that's the general formula that we're going to be using. So anytime you have a volume with some hollow cavity, you look at the outer radius and find the volume of the outer shape. You look at the inner radius, you find the volume of the inner shape, and then you subtract it, right? Because it's hollow. We want to remove that part. Right. Any questions so far? So outer volume minus the inner volume, which was hollow, so we remove that part. Okay, so let's substitute and work this out. So the volume is going to be the integral. This is along x, so we need the start of the shape, the x starting point, and the x ending point. Okay, so here, the x starting point is over here. What will that be? What's the starting of our shape? 0. And the ending of our shape, that's going to be that intersection point, right? What number is that going to be? So x squared equals root x. What do we get for x? Remember, the stuff's not going to be labeled for you. You need to figure out all the points yourself. Yeah? 1. Yeah. We go from 0 up to 1. Okay. Again, I just give you the graphs. I don't give you the intersections, all of that. You need to calculate that. Yeah, from 0 to 1. So that's the start of the shape at 0, the end of the shape at 1. So the integral goes from 0 to 1. Here we have pi common for both of them, so we can take that out. Okay, r out, that's the larger radius for the outside of the shape. So that's that vertical distance there. That's the y value. So it will be root x. That's for the outside part. Don't forget to square that. Okay, minus. And then r in, that's the smaller radius for the inside part. That will be x squared. That's on the smaller side there. And again, you need to square that. Okay, so that's all the setup done. So we've got the diagram, we've got the 3D solid, we set up the integral. From this point on, it's just a normal integral. Okay, so no more volume stuff. Okay, so let's expand out the squares and we can simplify. So we got pi, integral from 0 to 1, root x squared, that will just be x. X squared squared again, so that's x to the 4. Okay, this one's pretty straightforward. So we got the pi, half x squared minus 1/5 x to the 5 from 0 to 1. If we put 0, we just get 0, so we can ignore that one. So we just put 1. So this will be pi 1/2 minus 1/5. So we get pi. Law cross multiply, so we have 5 minus 2 over 10, so 3 over 10. Okay. And again, if you were given meters or something for the lengths, this would be units cubed. For us, it doesn't matter so much. Next semester, when you do the MATH162, it will matter a little bit more. But you don't need to write that for me. All right. Any questions for this first problem? Pretty easy. Okay. Number 2. Okay, so again, we've got the setup. We need to find all the endpoints and so on, set up the integral, and then evaluate. Okay, so we got the following. So we have y equals x squared, the line x equals 1. Let's put that in blue. So that's our bounded region. Okay, we want to rotate this around the y-axis. Okay, so that's the setup. We need to sketch this thing, set up the integral, and evaluate the integral. Now, this is going around the y-axis, so we need to think about that rotation. So we have y-axis, x-axis. Okay. That vertical line at x equals 1, if we rotate that around the y-axis, what kind of shape does that produce? Okay, so just the vertical line, just rotate it around. Cylinder. Yeah, we get a cylinder going around. So let's start with that. So we've got a cylinder. Okay. And what about y equals x squared? We rotate that around. It's going to make like a bowl kind of shape. Okay. But since it's inside the cylinder, we need to draw it inside the cylinder there on the right. So it's going to be something like this. Okay. So it's a cylinder, but that inside bit we've removed. So again, this bit here is solid. Right, that's like the walls of the shape. And that inside part there that I didn't shade, that's hollow. Okay, So again, between the y-axis and x squared, that hollow space there, that makes the hollow space in the shape. The blue space in the first picture there, that makes the solid blue part in the second picture. So again, this inside part here, this is a hollow cavity. So we end up with something like that. Okay, let's have a look at the cross section of this. Then we'll see what's the inner radius, what's the outer radius, and then we just substitute. Okay, so we're going to have some cross section. We just slice it across like that. Remember, we rotate around the y-axis, so the slices are also along the y-axis. Okay, so we end up with the following cross section. And again, this blue part, that's the solid bit. Okay, so we've just sliced it across. Okay, so this cross section here is going to have two radii. We're going to have an inner radius for the smaller circle and an outer radius for the larger circle. Okay, that inside part there that I didn't shade in, that's the hollow part. Okay, so let's go back to the first picture. So the smaller circle is going to have the inner radius. So that will be from the y-axis to the parabola. That's the smaller radius. R in for the smaller radius. Then from the y-axis to the line x equals 1, that's the larger radius. That will be R out. That's the larger one. Everyone see that? Smaller radius for the smaller circle, and then the larger radius for the larger circle. Any questions with that? All good? Okay, so let's set up the integral. So we have the integral from somewhere to somewhere. We've rotated this around the y-axis. So we're looking for the bottom of the shape and the top of the shape, okay, because it's vertical. So the bottom of the shape, what y value is that? 0, okay, because we're looking for the y value, so it'll be 0. And the top of the shape? 1, yeah. Because if x is 1, the top of the shape there will be y is 1. The pi we can take out. Then we need the outer radius squared. The outer radius was just 1. It's just fixed, constant 1. So we have 1 squared minus the inner radius. What's that going to be? Root y. Very good. Because that radius is an x value. So if y equals x squared, then x equals root y. And then we need dy, again, because our cross sections are along y. Okay, everyone clear on that? Okay. So let's simplify this, and then we can evaluate. So we have pi, integral from 0 to 1. 1 squared is just 1. Root y squared is just y. dy. Yeah, so we have pi y minus half y squared from 0 to 1. If we put in 0, we just get 0, so we can ignore that. Then we have 1 minus a half. That's just a half. Okay. Everyone clear with this one? So we had rotation around the x-axis. So the radius will be the y value. Rotation around the y-axis. So the radius will be the x value. Okay. Any confusion before we carry on? Oh, good. Okay, so the next one, we're going to look at what happens when we shift the axis of rotation. So far, we've only been looking at the x-axis and the y-axis, but we could also rotate around any axis, right? It doesn't have to be x and y. So here's a little bit different. So we've got the following setup. So we have y equals x squared. That's going to look like this. Okay, so that's our shaded region again. We're going to rotate this not around the x-axis or the y-axis, but around the x equals minus 1 axis. So let's put that in green here. Okay. So we're going to treat it like the y-axis because it's vertical. Okay, so that's going to be the same. But now the way we measure the radius will be different. Because previously, if we look over here, we saw that the two radii were coming from the y-axis to the shape, right? Because that was the center line. In this case, our center line is not the y-axis, but it's x equals minus 1. It's a little bit different. So we're going to draw the two radii and then work out what that's going to be. So let's do the inner radius first. That will be from the axis to y equals x, because that's the smaller distance. So that's r in. What about r out? That will be from the axis to the y equals x squared, right? That's the outside radius. That's r out. Okay. And notice that the radius will now be shifted by 1. So previously it was from the y-axis. Now we shifted it by 1, so we need to include that in our calculation. Okay, so let's look at r in. So this distance will be from the line x equals minus 1 to the y-axis. That distance is 1. So it's going to be 1 plus, because now we're going a bit further than that, from the y-axis to y equals x. What distance is that going to be? The distance there is x, right? Okay, it's x. But remember, this is rotated around a vertical axis, so we need it in terms of y. So that distance is x there, but x equals y, so it will be 1 plus y. R out is going to be the same thing. Look, we've shifted it by 1, so we need to add 1 to it. So it's going to be 1 plus. That horizontal distance left over is x. Okay, but we need it in terms of y, so it will be root y. Good. Okay. Remember, whenever it's a vertical axis, everything must be in terms of y. So the radius is an x value, but we must write it in terms of y. Okay, so let's substitute. So volume equals pi integral. We need the bottom and the top of our shape because we're going along y. So the bottom of our shape will be 0. Good. And the top of our shape? 1. Okay. So now we need the outer radius squared minus the inner radius squared. So this will be 1 plus root y squared. That's for the outer part. Minus the inner part. That's just 1 plus y all squared. Again, dy, because it's we're stacking them vertically. So this will be pi integral 0 to 1. Let's expand this out. So we have 1 plus 2 root y. Let's write this as y to the half. Plus root y squared. That's just y. Minus 1 plus 2y plus y squared dy. Okay, so we have pi integral 0 to 1. We have 1 minus 1, so we can get rid of those. Then we have plus y minus 2y, so minus y. Plus 2y to the half. And then we still have that y squared in the brackets there. Yeah, always try to simplify before you get to that integration part. Integrate, so pi minus 1/2 y squared plus, okay, add 1 to the exponent, 3 over 2, divide by that, 2/3. So we have 4 over 3, y to the 3 over 2, minus 1/3 y cubed from 0 to 1. If we put in 0, we just get 0, so we can ignore that one. Let's put in 1. So we have pi minus 1/2 plus 4 over 3 minus a third. That will be pi. 4 over 3 minus 1 over 3, that's just 3 over 3. So 1 minus a half, no, that's just a half. Yeah. So we have something like that. Okay. Any questions for this one? Okay. Okay. Please make sure you can do these problems with that shifted axis. So shifting a vertical axis or shifting a horizontal axis. Okay, you need to be able to do that. In the tutorials, I think there's like 5 or 6 problems with the axis shifted. Okay, so plenty of examples there. Any questions before we move on? Okay. Okay. Last one for the washer method, then we'll have a look at the shell method. Okay, so we have the following setup here. So we have y equals 2x. Y equals 3 minus x. Okay, and we're looking at this part over here. Okay, and we want to rotate this around the y-axis. Okay. So let's work out some things first. We're rotating around the y-axis. So we're going to go from the bottom of the shape to the top of the shape. We need those y values. So the bottom of the shape is pretty easy, y equals 0. But the top of the shape, we need to find that intersection point. Okay, that point at the top there, we're going to need to know that. So let's set these two equal and then find that y value for the top. So we're going to have 2x equals 3 minus x. Okay, so we're just finding that intersection point there. So that means we've got 3x is 3, so x equals 1. Okay, that doesn't help us. We need the y value. So if x is 1, y will be 2. Yeah, that's what we need. Okay, so here this is y equals 2. Okay, so from bottom of the shape to top of the shape, that's covered. Next, we need the inner radius and the outer radius. So we're going from the y-axis out to that region there. The smaller distance, that will be the inner radius. The larger distance, that will be the outer radius. So we've got here, so this will be r in for the inner radius. And then going out to that second line, that will be r out. Okay, so we've got inner radius, outer radius. What are those going to be? So that horizontal distance will be in terms of x. But remember, we need to write it in terms of y. So let's do that quickly. So we have r in. There's no shifting or anything, so just normal. So the inner radius, that was y equals 2x. So x will be y over 2. That's the radius. R out. Okay, so y equals 3 minus x. We need x. So that will be 3 minus y. Good. Okay, so we have everything for the integral. Okay, let's sketch this first, then we can evaluate the integral. So it's not too difficult. We just need to imagine what's going on. So this line, y equals 2x, we're going to rotate that around the y-axis. It's going to make an upside down cone. Everyone see that? Okay. Then y equals 3 minus x, we rotate that around. That will be like a normal cone, but it's cut off a bit. Okay, so let's see what this looks like. So the y equals 3 minus x, it's kind of the bottom bit of a cone because it's not extended up. So it's going to look something like this. Okay, that top bit's kind of cut off there. And then that hollow part from y equals 2x, that will be an upside down cone inside the shape. So it will look like that. So those two triangle bits on either side, that will be solid. So all of this bit here is solid. And then that upside down cone in the inside part there, that's the hollow space. So we end up with this kind of bowl shape. Did everyone see how we get that? No. Okay. Let's do a little diagram over here. Okay, so we got these two lines here. Okay, so I'm just extending that second one a little bit. So we have y equals 3 minus x. Okay, if we include that whole line, even the dotted part, what shape do we get? We did this last week. It's a cone. Okay, y equals 3 minus x. If we include that whole line, it's going to be a cone. You see that? That's a cone. But we're not including that dotted line. So that top part with the dotted line, we're cutting out. So let's do that in red here. That whole bit there, we're cutting off. So we look back at our cone and we chop that top bit off. You see that? Okay. And what about that inside part? So let's put that in green here. So we take that line, we rotate it around. It's also a cone, but it's upside down. So it's going to look like this. Right? Upside down cone. That's going to be inside that other shape that we got there. So it will be like this. That's this green part inside here. Okay. You see that now? Okay. And then this blue part here, that's this blue part here. Okay. Everyone see that now? Okay. So let's set up the integral now. So the outer radius is 3 minus y, the inner radius y over 2, and we're going from 0 to 2. So the volume, that's going to be pi, we can take out, integral from 0 to 2. Outer radius, over there, 3 minus y. Inner radius, y over 2. Squared dy. So this will be pi, integral from 0 to 2. Let's expand this out. So we get 9 minus 6y plus y squared minus y squared over 4. Okay, we can simplify a little bit first. So 9, we can keep there, minus 6y. Then we have 4 over 4 minus 1 over 4, so that's 3/4 left over. Okay, so this will be pi 9y minus 6 over 2, so that's 3y squared, plus 1/4 y cubed from 0 to 2. So it'll be pi. If we put in 0, we just get 0, so we can ignore that one. Let's put in 2, so 9 times 2, it will be 18. 2 squared is 4, so we get 12. 2 cubed, that will be 8 over 4, that will be 2. Okay, 18 minus 10, so 8. Okay, again, the units cubed, you don't have to worry about that for me, but please, for that math 142, right, they might be a bit more strict with the units. Okay. Any questions for this one? All good. Okay, so just to summarize the washer method, remember you're doing a slice across. It's going to be an outer circle with an outer radius, an inner circle with the inner radius, and you're just subtracting the two. So outer volume over here, okay, this outer volume with the outer radius minus the inner volume with the inner radius. Okay, very easy to remember. But for the tests and the exams, these equations will be given. You don't need to remember them, but it's pretty easy. So the volume equations, and then later on, the moments of inertia, length of a curve, and surface area. Those will be given. Okay. Yeah, it's too many equations to memorize, so I'll give you a little formula sheet. But if you do memorize them, that's fine as well. Saves you looking for the formula. Any questions with that? Okay. Right. Any last questions before we go into the shell method? Okay. Okay. The shell method. Okay, so we're going to start with the simple example again, just to get the idea. We'll derive the formula, and then there's another 3 examples to go through. Okay, so let's say we have the following shape, the following region here. So we have a little bump here. That's given by y equals x2 minus x. Okay, so we've got this region. It's a shifted parabola over there, and we want to rotate this around the y-axis. Okay. Now, this looks very similar to the washer method, because we have our axis. We could look for the inner radius and the outer radius, and we'll see that's going to cause some problems for us. So if we were just to use the washer method, this would be our inner radius, right? Because it's from the axis to the shape. And then the outer radius will be from the axis to the outside of our shape. Okay. But remember, those distances are the x values. But here we have y as a function of x, and we want to solve for x. That's going to be a little bit difficult to do, right? Because we have to invert it to solve for x. So in these cases over here, it was pretty easy. We had y equals 3 minus x. We just solved for x. Quite easy to do. Over here, not so much. Finding those x values a little bit more difficult. Sometimes it's actually impossible because the function's not invertible. So we put a little warning here. Very difficult, or sometimes even impossible, to solve for x. For the R in and R out. So in those cases where it's difficult or impossible to solve for x, we need something else. And that's going to be the shell method. So the way this works is we think about this 3D shape, and instead of cutting it up into disks and washers, we're going to break it up into cylindrical shells. Okay, so we call it the shell method, but like the full name is the cylindrical shell method. Right, but it's always cylinders, so we just call it the shell method. Okay, so what's the idea? So let's see what this looks like in the full 3D, and then we're going to see how are we going to break it up into these cylindrical shells. So it's going to look something like this. Okay. Something like that. Okay. And how are we going to break this up? So we've got this radius going through this axis going through the middle here. And we're going to imagine a cylinder going around. Okay, the cylinder has a little bit of thickness to it, so it's something like that. Okay, does everyone see that? So it's a cylinder, but it's slightly thick there. What we're going to do is imagine a number of these cylinders going around this thing. If we know the volume of each of these cylinders, we can add them up, and that's going to give us the total volume. Okay, so the idea is something like this. Okay, so imagine we've got this one cylinder. We're going to add a few more. So we've got a bunch of concentric cylinders going outwards. Okay. So they all have different heights, and we have them going concentrically outwards. Concentric cylinders. The idea is to take this 3D shape and write it in terms of these cylinders here. So we're going to draw it in terms of the cylinders. We're going to find the volume of one of the cylinders and then add it up. Okay, so let's look at one of them. Let's say this middle one over here. Again, it's hollow on the inside. It's only that outside bit that we're interested in. Okay, so again, inside here, that's hollow. Okay, so how do we work out the volume of this? Okay, the radius of the cylinder, we know what that's going to be. It's from the y-axis going outwards, so the radius is x. Okay, remember, the y-axis is going through the middle from this first picture. So we've got the y-axis through the middle. This radius here is x. Okay. What will the circumference of the cylinder be? The radius is x, the circumference going around. What's that? 2 pi x. Okay, 2 pi x, that's going around. What about the height? Remember how these cylinders are being stacked? This height here, what's that going to be? Yeah, it's this distance here from the bottom of the function to the top of the function. What's this height here? Yeah, this bit, this height here, what's that? Y. It's just the y value. That's the height. Yeah. So what's the volume of the cylinder going to be? Okay, the volume of a cylindrical shell. What's that? You've seen this before, right? Volumes of cylinders and that. Okay, what's the volume? So we got the circumference, we got the thickness, we got the height. What's the volume? You've seen cylindrical shells before, right? You got an outer cylinder, inner cylinder. We want the volume of the shell part. Okay, so it's going to be the circumference, 2 pi x, times the height, right? That gives you the volume there. And then the thickness is dx. Okay. Have you seen this before for a shell? Yeah, we'll draw a little picture here. So you got something like this. Okay, so if you've got the radius, the height, and then this thickness, let's call that delta r. Then the volume, 2 pi r h delta r. You've not seen that before? Okay, well, please write that down. You will need to know that. Okay, so if you've got a cylindrical shell with a little bit of thickness to it, that's the volume for it. So it's 2 pi r h times the thickness of the shell. Okay, so that's the volume of one of the shells. And now we're adding it up, going outwards for the x radius. So that's going to be equal to the integral from a to b, 2 pi xy dx. Okay, so we're just adding up all of those cylindrical shells going outwards. Okay, so let's use this formula we derived now for that first problem. So let's redraw this. Okay, so we have y equals x2 minus x. We're rotating this around the y-axis. Let's draw in these cylinders. So it's going to have the height being y, the thickness is dx, it's a little bit along x, and then the radius is x. Okay, so let's fill that in here in pink. So we've got something like this. So at that point x there, we can draw ourselves a cylinder going around. Okay, and then maybe at another point, we can draw another cylinder going around. I don't want to get this too messy. I don't know, maybe that's a bit messy. Can you see the pink cylinder and then the blue one outside? Okay, I don't want to make it too messy, but the idea is we're stacking these cylinders going outwards. Okay, maybe let's get rid of the blue one. Okay, so we have that. Now we want to add up the volumes of all of these. So the volume is going to be the integral. Now, it's not going to be the start of the shape to the end of the shape like we had before. The integral is going to be from the inner radius to the outer radius going along as we are stacking these outwards. So what is the inner radius for this? So it's the smallest x value towards the center. What will that be? So the starting x value on the inside is? Oh, we have y equals x2 minus x. What's the first x-intercept? First one over here. What's this? 0, yeah. And then we're stacking them going outwards. So what's the larger radius? That x-intercept at the bottom there? 2. Okay, so we have a cylinder at the center there, and then the cylinders go out and out until x equals 2. That will be the largest cylinder. So we're going from 0 to 2, 2 pi x times the y value, that's the height of these cylinders, that will be x2 minus x. So this will be 2 pi is a constant, we can take that out. Integral from 0 to 2, we've got 2x squared minus x cubed. That will be 2 pi, 2/3 x cubed minus 1/4 x to the 4 from 0 to 2. If we put in 0, we just get 0, so we can ignore that one. Let's put in 2. 2 cubed, that will be 8, times 2, that will be 16. And then 2 to the 4, that will also be 16. Okay, you can do a bit of cross multiplication. You can simplify that. All right. Any questions for this first one? Okay, so just to summarize this first one. So we've got these cylindrical shells. They're going outwards with larger and larger radius. The start of the integral will be the smallest radius. So here we're starting at 0. And then the shells get larger and larger as you go out. So the ending radius will be at 2. That's the largest x value. That's the widest cylinder. Then the height of the cylinder is whatever the function value is at that point. So here the cylinder starts at height 0, then it goes up to a maximum height, and then the cylinders get smaller going out. Okay, then we just add all of them up with the integral, and we get our answer. Okay, any questions? All good. Okay, next one, number 2. Okay, we have the following setup. X equals 1. Y equals x squared plus 1. Okay, so we've got this bounded region. So it's below y equals x squared plus 1 between x equals 0 and x equals 1. We want to rotate this around the y-axis. Now again, we can look to see what happens when we use the washer method. We need the inner radius and the outer radius. Now here it's a little bit confusing because if we look over here, there's no inner radius because it just stops at 0. And then the outer radius is 1. But if you look slightly up, now the inner radius is this part and the outer radius is this part. You see how it changes. So for that bottom portion, R in is 0, R out is 1. And then for that top portion, R in will be up to the parabola and R out will be 1. Right? It changes. So you're going to have to, if you want to use the washer method, you're going to have to split this into 2 parts. Okay, you'll have the bottom part and the top part. You can do that. We're not going to do that. Maybe you can try it for homework. What we're going to do instead is use the shell method. Okay, so let's redraw this and see what the shells are going to look like. Okay, so we have y equals x squared plus 1. Okay, so going along the x-axis, that's going to be the radius for the shells. The height is whatever the parabola value is. And then they're going to loop around the y-axis. Okay, so it's going to be something like this. So that's going to be the little side wall of the shell. We loop this around and we get a cylinder. Okay, so that's going to be one of the shells. If we picked a different point, we're going to get a different shell. For example, here, if we can do it in blue. Okay, so in blue there, we get a larger shell on the outside. Okay, so let's set up the integral for this. So we're going to have the volume is equal to the integral. Remember, the integration is done along the radius of these shells. So the starting radius will be at x equals 0. That's the smallest shell. And then the widest shell there is at x equals 1. Right? They're going outwards. So it's going to be from 0 to 1. Then we have the circumference, 2 pi x. And then the height of the shell, that will be from the x-axis up to the parabola. That's the height. And then dx, that's the little shell thickness. Okay, so it's all set up. Let's evaluate the integral, see what we get. So 2 pi, that's a constant. We can take it out. Integral from 0 to 1, x cubed plus x. So this will be 2 pi. X cubed, that will be 1/4 x to the 4 plus a half x squared from 0 to 1. So 2 pi. If we put in 0, we get 0, so we can just ignore that one. Put in 1, we get 1/4 plus a half. Again, units cubed, but we don't really need that. Okay. Any questions for this one? All good. Okay. Number 3. We've got the following setup again. So we have the line, the curve, natural log of x. Okay, so that's our curve there. And we want this between x equals 2 and x equals 4. Okay, so that's going to be this portion over here. And we want to rotate this around the y-axis. So let's see how we can do this. So we can't really use the washer method. There's no simple inside radius, outside radius, so that's not going to work. So we have to use the shell method. So let's set up what the shell is going to look like. So let's say we've got our little cylindrical shell starting there. This little pink strip here, we're going to rotate that around. That's going to give us our shell. Something like that. Okay, so we see that the radius of the shell here is going to be x. The starting radius will be at x equals 2, and the ending radius will be at x equals 4. Okay, so that's the radius going outwards. The height of the shell will be the natural log. So it's the distance from the x-axis up to our function. So that's just the natural log of x. And then the thickness, just dx. So let's set up the integral. So it's the integral from the starting radius. So on the inside, the shell is going to start at x equals 2. And going outwards, the widest shell there will be at x equals 4. 2 pi x, that's for the circumference going around. Then the height, like we said, that's the natural log. And then the thickness dx there. Okay, so that's all set up. Let's evaluate this. So 2 pi, that's a constant. We can take that out. Okay, we've got a product of two functions, so we have to do integration by parts. One of them is an inverse function, so that's going to be u. So again, like I said before, all of those integration techniques we did before, they can show up here. Okay, like with this one. So we need by parts. So we're going to have u equals the natural log of x. dv is x dx. So du 1 over x dx. V half x squared. So this is going to be equal to 2 pi uv from 2 to 4 minus 2 pi integral from 2 to 4 v du. Okay, so we get 2 pi. If we substitute 4, we're going to get 4 squared. That will be 16 over 2. So that will be 8 natural log of 4. Minus 2 squared, that will be 4 over 2. So that will be 2 natural log of 2. minus 2 pi 1/4 x squared from 2 to 4. So we get 2 pi 8 natural log of 4 minus 2 natural log of 2 minus 2 pi. If we put in 4, 4 squared, there'll be 16 over 4, there'll be 4. Minus 2 squared, there'll be 4 over 4. That's just 1. So we get 2 pi 8 natural log of 4 minus 2 natural log of 2 minus 4 minus 1, there'll be 3, so we just get 6 pi. Okay. Pretty simple, but again, please make sure you know your other integration techniques. So for this class test 2, the scope doesn't explicitly say integration techniques, like for the class test 1, but you see, they can show up, right? Use substitution, integration by parts, trig integrals, all of that can show up depending on what these functions look like. Right, if I give you some trig functions, it's probably going to be something with the trig integral. Okay. Or like this with the inverse function, there'll be some bar parts. Yeah, it'll be something like that. Any questions for this one? All good. Okay, the last one, a little bit challenging. I'll leave that for homework for you to try. So this will be the shell method with a shifted rotation axis. Okay, like we did before with the washer method. So we have two curves, y equals x squared. That. So y equals x squared. Y equals x cubed. Okay, so that's our bounded region. So it's above y equals x cubed, but below y equals x squared. And we want to rotate this around the axis x equals 1. Okay, so it's a little bit different. You need to work out what the radius will be in this case. So you can't measure the radius from the y-axis, so it won't be x like we had before. The radius will be from that pink line. Okay, so just be a bit careful with how you measure that. I'll give you a little hint. So this total distance here, that's 1. Okay, that total distance there is 1. And like we had before, this distance here, that's still going to be x. Okay, so that's your hint for that. Right. Any questions for the homework? So try this out. Then tomorrow we're going to do the mixed problems. So for these ones, the first 4 I said washer method. These ones I said shell method. Tomorrow they're going to be mixed. So I'm not going to tell you what method it is. You need to figure it out. Sometimes you can do it multiple ways. It's best that you learn how to figure out which one's the easier one to do. Okay. For example, this one you can do using the washer method and the shell method. Maybe the shell method is easier to do. Maybe the washer method is easier to do. You'll need to figure that out. Okay. Then next week, we're going to be going on to moments of inertia. You'll be covering that in the 161 and the MATH162 next semester. Okay, so the one we're doing is not so difficult. The 142 is a bit more difficult, but hopefully I can prepare you for that. And then just a little note. So when we do the moments of inertia, it will be something like this. So we're working, you know what moments of inertia is, right? You got some solid, you want to rotate it. How difficult is it to rotate? That's given by the moment of inertia. For some 3D shape, it's given by this formula over here. Notice at the end there we have dv. That dv depends on what shape we have. So calculating this, that dv could be the dv from the disk method, could be from the shell method, could be from the washer method. Depends on the 3D shape. Okay. So please do not, learn and delete for the next quiz, and then when we get to inertia, you have to relearn all of this. Okay, so please, disk method, washer method, shell method, please keep that in mind for next week as well. Okay, so just because we finished with it now, it doesn't mean it's gone. Okay, so next week, we do need to know those still. So disk method, washer method, and shell method. And again, I don't tell you which one to use. You need to figure that out. And then last thing, the quiz. Next week, Monday's a holiday, so we're not going to have a quiz then. The quiz will be the following week, which means the quiz will be on the stuff we've done this week, the disk method, washer method, shell method, and the stuff we're doing next week on the moments of inertia. Okay, so for the written part, it will be one question on just finding the volume, 5 marks. So no sketching and stuff, just the volume. And then one question on the moments of inertia, another 5 marks. Okay, that will be the 10 marks for the written. The MCQ, that will be mixed up between the two. Okay, any questions for that? All good. Okay, and then the class test 2, I'll give you some more details later on.